Hi, my name's Kelsey Woods.
And my name is Ayushi Verma, and today we are presenting to you our project on health insurance. This is our final project for the machine learning class that we've done this semester.
So our problem statement and data set was provided by Kaggle. It's the data set on medical costs per personal, which I just considered based on like the explanation provided by Kaggle to be the cost per family and the associated factors that affect the cost per family, such as age and BMI. And we were looking to see what factors were most highly associated with a higher insurance plan cost, which is very important these days.
So we downloaded this data. It was a comma-separated value file, a CSV file, and we read it into Python using a pandas data frame. And for the data cleaning process, we removed NaN, which is not a number, values, null values, missing values. We removed duplicate rows and duplicate values. We imputed the NA values using the mean value of the column just to fill in those blanks. And finally, to prepare for the machine learning process, we performed some labeling coding to change the categorical data to a numerical data type. And so here we have the correlation matrix that we obtained to look at how correlated the variables are to each other. So some of the variables, well, these are the only variables in the data set, are age, sex, BMI, children, smoker, indicating whether or not the person is a smoker or not, region, which region they're from, and finally charges, that's money in terms of dollars. And we see that the highest correlations are between smoker and charges, which implies that if you're a smoker, it's going to be very highly correlated that you will also have insurance charges or medical charges. There were also correlations between BMI and age and charges. So BMI is correlated with charges, age is correlated with charges. We saw there was a negative correlation between charges and sex, negative correlation, well, for all of them actually, sex with region, smoker, children, BMI, and age. So looking into the variables a little more, the main variable, of course, we have is the insurance charge, the cost. And so looking at the histogram on the left, we see that there is, well, it's very left skewed with a higher concentration of, people who are charged up to $30,000 roughly. That's how it's skewed. And then there are some, there's a little more data laying on towards the right. And then we have a box plot to represent this data a little more neatly. And then again, we see that the majority of the data that's, the first interquartile range and the third interquartile range is concentrated between, I want to say 5,000 and 20,000 very roughly. And then there are quite a lot of outliers beyond the $35,000 charge amount. So again, this data set is very left skewed in terms of insurance charges. And then looking at our target variable of interest, BMI, that's body mass index, we see that this data is more uniformly distributed, very similar to a Gaussian bell curve. And it is roughly distributed between 20 and 45 BMI. Again, the mean of this data we see is around 30, which I think according to official records, having a BMI of 30 is classified as overweight. So that seems to be the mean of this particular data set. And then there are a couple of outliers beyond 46, 47 BMI. Yep.
Which BMI is supposed to correlate to your percent body fat, although it does not do that very well.
No.
So basically, the NIH and other health official groups are trying to change that, but it's basically indicating what your supposed body fat should be for the BMI overall. Just a little tidbit.
Yeah, I mean, it doesn't even capture like relevant information like your metabolism or there's a ton of other factors that play into your health per se, and your height and weight, which go into the BMI measure, are not very accurate representatives of that factors.
Yeah, it also doesn't take into account muscle mass either.
Exactly.
Which is a huge thing.
Yep, because more muscle burns more calories, or more energy. Anyway, so here we're looking again at a scatter plot of those two variables, BMI on the x-axis and the total charge or cost on the y-axis. And we see that there is a very correlated distribution, I want to say, for BMIs between about 20 to 45, and they have correlated charges of about ranging up to 15,000. And then there's this sort of spout that goes off on a linear upwards trend that kind of, to me, indicates that the higher your BMI goes, it is likely that you will also have higher cost charges.
So we also did some machine learning algorithms because, of course, this class is machine learning. The 5 algorithms we used were linear regression, random forest, SVM, lasso regression, and decision tree. We did a split of 0.2 to 0.8, and we did a random state of 42. We also use scikit-learn for the machine learning. So for the optimization, you can tell that the gradient boosting regressor, number 4 here, had the best adjusted R-squared. It was clearly a better R-squared by a good amount, with 0.78, and then numbers continued to be second and third, which basically, if I were to rank them by adjusted R-squared, which is my preferred value for correlation, I would say gradient boosting regressor, linear regression, lasso regression, decision tree regressor, and then SVM is just completely missing the mark with an inverse correlation. So for the hyperparameter tuning, the ridge regression and the lasso regression both had the same scale, and they had the same X and Y axis as well, with true values being X and predicted values being the Y. They are the exact same with no difference, which indicates that we definitely need to tune a little bit more to get a better value and get more understanding, because it looks like they're doing about the exact same, which you could tell. We'll show you our code as well, but they had very similar expected hyperparameters as well, because we did a grid search for that as well.
And so, as Kelsey pointed out 2 slides ago, we will conclude, we'll show you in the conclusion, but the support vector machine model did not perform the best. And the reason for us saying that is because of this slide over here. So I will walk you through what is going on here. It's a very big slide, I know, but let's get through it. So these metrics, okay, taking a step back. We did a bunch of regression models on our data to predict, the charges that it's going to cost someone, predicting that. And in order to evaluate the 5 models that we did, just out of the box, no hyperparameter tuning, no optimization, no graded boosting, just scikit-learn out of the box. There are some metrics that we need to use to evaluate the goodness of the predictions. So did my model actually predict a value that is, reasonable, in line with the actual values that it should have been? So the first graph, the one called May comparison, that's the one with the red bars. MAE, that stands for mean absolute error. It measures the absolute difference between the actual values and the predicted values. Having a lower value is better because it just indicates that there's not too big of a difference between the actual value and the predicted value, which is ideally what you want. However, like we're seeing for the SVM, the support vector machine bar, if there is a massive difference between your predicted value and your actual value on average, that does not speak very positively to your model. Another thing that I would like to point out is if you're looking at the y-axis for this graph, it has a order of magnitude that is roughly equivalent to the actual data. So in the actual data, when we were looking at charges, you could see that the data was, 20,000, 30,000, 50,000, so on and so forth. So it was the order of magnitude for that data is, in units of thousands of dollars. The errors that we're seeing here for the mean absolute error is also in terms of thousands of dollars. So if your value, your actual value, if that's, $50,000 and it has a mean absolute error of 6,000, for example, that kind of makes sense. That makes intuitive and physical sense that, okay, for a charge of 50,000, you're getting a error of about $6,000. So just something interesting that I wanted to point out. Okay, so the next graph, the yellow one, is MSE, mean squared error. So this metric evaluates the squared difference between the actual values and the predicted values. And the reason that it's squared is to A, remove any negative values that may arise, and B, to sort of gauge the effects of the outliers on this data set. So again, for this metric, we want, the lower the better. So we see here that the gradient boosting regressor has the lowest mean squared error, and support vector machine model has the highest MSE, which is not a very good metric. Noting the units on the MSE, it is, 10 to the 8th power. That is a very high value. And so we look at the RMSE, which is the next graph, the green one, which is root mean squared error. So this one brings it down to more, comprehensible order of magnitudes. It is simply just the squared root of the MSE. Again, we're seeing the same trend being reflected where gradient boosting model is performing the best and support vector machine is performing the worst. So down at the bottom, the blue graph is comparing the R squared. So the R squared is a metric which evaluates the variability that is explained by the model. So we were initially, we learned that the R squared values should ideally be between 0 and 1, where 0 means that the model is not explaining any variability at all in terms of the features of the data set, and 1 explains full variability in of the features in the data set. So we find that the decision tree regressor, the linear regression, lasso regression, and the gradient boosting regressor, they all range between 0 and 0.89, which kind of tells you how much the model is taking into account the other features in order to generate its predictions. On the other hand, the support vector machine model has a negative R squared value, which we had to look through the scikit-learn documentation to learn that, yes, that is actually possible. And that just, I wasn't really sure what to make of it, but I think it means it's a terrible performing model. The adjusted R squared value is just a slighter, it's adjusted. But we see the same trends being reflected across. So this graph over here, on the previous slide, we had explained the evaluation metrics for out-of-the-box scikit-learn model performances. However, like Kelsey will soon explain, we also did other things like optimization, hyperparameter tuning, and cross-validation. So on this slide, we're actually comparing the metrics that we saw on the previous page, the normal models, compared to the cross-validation approach. So the first one, looking at the mean absolute error, the red bars are the normal model results, and the yellow bars are cross-validation model results. And apart from support vector machine and lasso regression, actually, we see that the cross-validation actually performed worse than the normal one. The support vector machine and the lasso regression did not there was no difference at all between the normal approach and the cross-validation approach, which I thought was pretty interesting. We actually see this trend being reflected for the other evaluation metrics as well. Looking at mean squared error, root mean squared error, and R squared. Yes.
All right, so we're doing a model evaluation and comparison. We did this for all 5 of the models that we looked at, but we wanted to specifically highlight these 2, the linear regression and the random forest. So if we look in the left for the linear regression, we see the true values are pretty scattered. The fitting predictions are about the same as the overfit predictions, which is very frightening. To be honest, overall, we don't really want that. We would rather have the true values and the fitting predictions make a little bit more sense together. But if you look at the random forest, this is more ideal, but it's still not ideal. Everything from true values to fitting, underfitting, overfitting are all pretty on top of each other. Which if we had the blue, which is true values, and the green, which is fitting predictions, on top of each other, that would be ideal. But underfitting and overfitting are very close to each other as well, which could indicate that the model isn't doing what it's supposed to be doing. But it also indicates that, like, if you see how clustered these groups are, it can really indicate that the overall values are doing what they're supposed to be. But underfitting and overfitting is a very fine line. We also did a linear versus lasso regression graph with true values on the X and predictions on the Y. The linear is these like dashes going all the way up. And the lasso regression is staying around the 10,000 to 20,000 prediction area with true values scattered along the X-axis. So linear is doing exactly what we expect it to. Lasso regression is basically doing its own thing with the number of predictions provided, which means we could alter the model to receive different results. So the decision and conclusion, we did gradient boosting was the best model, SVM was the worst. The hyperparameter tuning and the gradient boosting significantly helped improve the performance of the model because hyperparameter tuning lessens the effect of overfitting and underfitting. It can lead to improved accuracy, precision, recall, and other performance metrics, and it can reduce time and need for resources. And then there's gradient boosting, which combines the strengths of multiple weak learners by using other models that have strengths in those weak areas. It also captures complex patterns, which include nonlinear ones, and it helps with feature selection and managing unbalanced data, which is likely the problem we're dealing with. And we could definitely use more hyperparameter tuning and boosting as well. But the gradient boosting did perform the best, and we did find the ideal models through a grid search, which I will show in a second.
In the meantime, while you're switching over, Kelsey, just one thing that I had wanted to mention was that the reason we didn't use evaluation metrics like, accuracy, precision, recall, sensitivity, and F1 score is because those are metrics used to evaluate classification models. Also confusion matrices. Those are all for classification models. However, this is a regression problem, which is why it required things like MAE, RMSE, R squared, so on and so forth.
All right, so I can go through our code a little bit. We imported a lot of our packages at the beginning, just because we've done this before, we know what we needed. We imported the data, did a check of how much, checking the data content. We also encoded everything one by one rather than hot one encoding, because scikit-learn does not tend to like hot one encoding very much. We also looked at the data again once we encoded it, looked at the shape to make sure we hadn't added a little column or a row where we didn't mean to. And then we converted to numeric so that we could really do some good machine learning with it. Looked at the info again to make sure we had the right data types. We filled the NA values with the mean, pretty standard for the field, dropped the duplicates. Then we did a correlation matrix, which we already looked at, so I will not put you through that again. Did a few more EEAs, the charges, the BMI, which you've already seen, the scatter plot. This is, now that we have a clean data set, we wanted to look at the machine learning. So this is us defining exactly what our variables are to compare them all at the end.
It's a function that we wrote to calculate the adjusted R-squared because scikit-learn has functions to evaluate the MSE, MAE, and R-squared, but not for the adjusted R-squared. So that's why we wrote a custom function.
We dropped charges for the X, kept it for the Y, which we could show you that basically it just looked like charges for the Y and the rest for the X, which is why it might be unbalanced. Looked at the info again. Shape is the same, which indicates everything's as it should be. We didn't coerce, but we forced the variable type BMI to be an integer as well, just for the test train split, because it was giving us some problems before as its original type. We did a 0.2 versus 0.8 test size to train size in a random state of 42. And then defined some of the data frames to record metrics for each model and stage of analysis. These were basically the columns to write out for the normal results and then the cross-validation results. Here we did a decision tree regressor, which was our first model. Basically just plugged it into scikit-learn. We experimented with the random state a little bit. That's what gave us the highest values. And then we fit it to the X train, Y train, did a Y predict from the regressor, and then calculated these metrics from there, which here are the values that we received, which you'll also be able to see through the normal results that Ayushi had built out. We also did a cross-validation through here, which you get the overall values of everything with the cross-validation and without. So here are all the values. Then we did the same thing with all the rest of the models. We did a linear regression, for example, same exact thing happening. We basically just repeated the code, but made sure we adjusted for the model. We also did we defined the parameter grid for ridge and lasso, which we did a grid search for to find the best parameters in the model MFD, which we went over earlier. We did the support vector regression as well. Did the same thing basically over and over again to get what we got. And then here are the best parameters, best model, MSE. Basically just kept doing it over and over again to see what kind of values we were getting, and did it with the random forest. I would like to say though that we had to do random forest regressor and not regression, because it wouldn't let us do the model as the regression, because we couldn't evaluate using the same metrics. Continuing, we did the gradient boosting, same exact formula as before, but you do the GB regressor to fit. And then we did the underfitting and overfitting check, which we did with the linear regression. Here are the values. Random forest. Decision tree. SVR. Trying to hide my Boston accent with the R. And then the results. which the lovely she coded out for us. And then here's our conclusion discussion, which we already went over. Thank you, and please email us if you have any questions. We had a lot of fun on this project.
We did. Thanks.